Hi there, folks. This is Mr. Lois. Welcome to another exciting edition of HO Chemistry Flipped Classroom. This is about nuclear medicine. So we talked about just radiation in general last week, and so I just want to hit the highlights of some of this right here. Hopefully keep this kind of short and sweet. So here we go. Let's do this. So ionizing radiation, we talked about some of the different forms of radiation last week. Ionizing radiation is the radiation that is energetic enough to knock electrons off atoms, producing radicals. And we talked about alpha, beta, and gamma radiation. Those are all examples of ionizing radiation. Other types of like electromagnetic radiation, like microwaves and radio waves and that kind of thing, visible light, that's non-ionizing radiation. So things like cell phones and stuff, they carry their, and Wi-Fi signals and all that, they carry their information in the typically in the microwave region or below or somewhere in there, definitely non-ionizing radiation. So sometimes people claim that cell phones or Wi-Fi give them cancer or causes the problems. Seems unlikely based upon how low energy they are, even lower energy than even visible light. Keep that in mind. So if cell phones and Wi-Fi is dangerous, visible light should seemingly be even more dangerous. But what causes problems with radiation, there's a little bit of a misconception. I think if people think about it at all, they think it somehow like damages your DNA directly, like a beta particle goes in and damages DNA. And that could happen, but actually it's pretty unlikely because relative to other molecules, there's very, very little DNA. What it's more likely to do is hit something like a water and create some radicals, either a hydrogen radical or a hydroxide radical or both, I guess. And then those are the things that might go ahead and in turn damage DNA or do something like that. So basically alpha and beta and gamma are all useful in different ways depending on what you're trying to do from a medicine perspective. We talked about alpha particles, they can't penetrate very much, so they tend to dissipate all their energy in a small area. And they do a lot of damage but in a small region, whereas beta and especially gamma tend to zip through the cell quickly. You know, gamma radiation is going to leave your body pretty quickly. And so alpha particles are said to have greater ionization density. So they can do a lot of damage in a small area. And again, depending on what you're trying to do, you might want to use different things. So there's a couple of major ways that medicine uses radiation. One is in getting images, and the other is in treating disease. I talked a little bit when I was talking about radiation in general that we can use iodine to actually collect in the thyroid. And, well, I'm going to talk about that more later, but technetium-99 is a radioactive isotope. It's useful for imaging. It has a very short half-life of 6 hours, which is good. That means it's going to be gone and out of your body fairly quickly. Its half-life is so short that you actually can't, as a hospital, get a shipment of it because, you know, obviously by the time it leaves the factory and gets to you, it's going to be decayed. So they get molybdenum-99, which ends up being turned into technetium over time. So it sort of is produced on site. Yeah, I changed that to MO99 because it should be MO99. So the reasons that this is good is it has a short half-life, so it basically it's over and done with fairly quickly. It produces gamma rays, which leave the body without doing too much damage. They basically just zip right through you. It can be attached to several other things. When we talk about bioavailability, so maybe you can attach this molecule to something else and get it in a certain area of the body where you want to emit those. And then you can get an image with some kind of like gamma ray camera. Same with iodine-131 is also a gamma emitter. That iodine happens to be something that it collects in the thyroid. We talked about this a little bit already. So you can use it to either image the thyroid and get some images of the thyroid, or you can use it if you inject a large amount to actually kill thyroid cancer. MRIs is an application of the NMR technology that we talked about before the closure, where we're studying hydrogen atoms and how they behave. And they called it MRI, magnetic resonance imaging. They didn't want to use the word nuclear. They didn't want the radiation piece to scare people, even though it uses radio waves. So it's non-ionizing and totally safe. And so basically what you're doing is you're using the MRI to find water molecules, and because there's so many water molecules in the body, you can get very detailed images. So in this case, we're using radio waves actually to get super detailed images like this one. Big advantages over X-rays. You can see a lot of internal structure and things like that. I sort of hinted at the beginning of this that we're only going to talk about the things that I want to talk about and that I think are most relevant. So let's not talk about PET scan. You can read up on it if you want, but I'm not going to talk about it. Cancer, obviously, certainly a relevant and important topic. Basically, with cancer, what you got is you got uncontrolled cell growth. You got some cells in your own body that are growing out of control. Our cells in our body are supposed to grow when they're told to grow and die when they're told to die, and basically cancer cells don't do that. And, we kind of talked about the challenge with bacteria and viruses of finding things that harm the pathogen but not the actual cells. So with cancer, it's even more challenging because, these are actual human cells. So how do you kill human cells without damaging other healthy cells? Turns out to be pretty hard, and this is why a lot of the treatments, I dare say most of the treatments for cancer, come with some pretty bad side effects often. So we want to try to find, ways to maybe really specifically kill those cancer cells and do a little less damage to the rest of the cells as possible. You want to get things with short half-lives, like with the technetium. You want beta emitters and gamma rays to allow for imaging, so you can get maybe some imaging and some cell death at the same time. So, you can see and you can read through things yourselves about a couple of these isotopes that are used. Targeted alpha therapy is kind of interesting because, again, we're trying to target this to a specific location. This is especially useful when metastasis has taken place. That's when cancer cells tend to, or they can possibly spread their message of uncontrolled cell growth to other cells, and that's when things get really problematic. So if you have cancer all over your whole body, we can use this TAT therapy possibly, and they use radioactive lead-212, and they attach it to a specific type of antibody, and maybe it is known that this cancer cell has a certain type of antibody that the other cells lack. So basically the lead-212 will selectively attach to cancer cells, and then it's an alpha emitter. So it's going to bomb just that close region with alpha cells, and as we said, alpha particles rather. And as we said, alpha particles tend to not spread very far. So maybe you can attach to a clump of cancer cells, really zap those cancer cells with alpha particles and kill them, but leave the other cells unharmed. This is another one that's kind of similar where you use boron-10, which itself is not radioactive. So you give someone some boron-10, and then you zap them with neutrons, which aren't really harmful in particular. But then what will tend to happen is boron-10 will undergo or do some neutron capture and turn it into boron-11. Typo there. Now, boron-11 is an alpha emitter, so it will release alpha particles. So it's kind of killing the cancer cells that it's within. So the reason that this works as a little bit of a selective agent is rapidly dividing cancer cells tend to take up the boron-10 a lot more than other cells. So the cancer cells tend to have more of the boron-10 in them. The other cells don't have as much boron-10 in them. So the boron-10 ends up taking on neutrons, emitting alpha particles, doing a lot of damage in a short area, and hopefully just killing the cancer cells and limiting the damage. You can also use radiation from the outside. Cobalt-60 is a beta and gamma emitter, and it can, from an external source, it can zap. So, they know, okay, probably from an MRI, there's a tumor right here or whatever, and they can just kind of zap that area from the outside. It's called a gamma knife. This would be for a brain tumor possibly, where you wouldn't want to really cut into it necessarily with the brain and do some damage. I think people are generally familiar, very often someone has been involved with cancer. It's a very common disease. So I think we are familiar with some of these forms of side effects, but no matter what we try to do, like I said, there's this challenge of killing their cancer cells without killing the normal cells, but it's a pretty big challenge to do that. So there are going to be some side effects: losing hair, nausea, fatigue, sterility, especially if the treatment is near the reproductive organs. Radiation type treatment in those areas can affect the reproductive cells and cause sterility, and just various other things. But cancer is a very serious disease, so it requires some serious medication, and in the case of a more serious disease like cancer, we have to be willing to tolerate some of these more significant side effects. Okay, that's it. Got this puppy all done in under 10 minutes. Thank you for watching. Stay safe out there, and we'll see you around.